All right. I gave this talk at Career Day at my old high school, and I thought to just make a recording of it because I think other people might find it useful. And so, the goal of this talk is to describe to you what it's like being a scientist. There are some popular conceptions of what it's like being a scientist, and there's a real life of being an actual scientist. And so, the idea is to show you what the real life of a scientist is like. So some caveats. Um, this will be incomplete, right? Being a scientist is pretty complex, and I'm very simple, and the talk is short. And it will be biased. There are many careers, even within scientists, right? And my job is a particular one. So I think the thing to keep in mind is that it's not a map, right? So what I'm about to say is not to tell you how to become a scientist. It's just a view on where I am at, which is maybe you think of it as some distant mountain and the kind of stuff that I do that I see. So to give you some perspective and not a way to get there. Okay? So with that in mind, I organized this talk into 4 parts. I'll be talking about myself, and I will talk about scientists in general, and I will talk about the kind of stuff that motivate us and the actual work that we do. So let's talk about what motivates scientists in general. Well, we have some idea of what motivates scientists. One of them is to make discoveries about the natural world, but we can be more specific. So what kind of discovery they're actually useful? Well, the kind of discovery that are useful are the one that help make predictions. And so if I plant rice, I can predict that I will get rice. So what makes a good predictor? I would say it should be communicable and general, and it should be accumulative. So what is communicable? Well, if I tell you a way to predict the future, but you need to read 10,000 pages, it's not very communicable. And it should be general. By that I mean, if I tell you a way to predict the future, it should work for me, and it should also work for you. And lastly, I tell you some way to predict the future, you should be able to take my theory and accumulate and build on top of it. And so I will use some example. Here is Archimedes, a scientist that most of you would know, and he likes to use lever to lift heavy objects. And by doing some kind of math about how objects can be balanced around the lever, he developed the formula of the volume of a sphere, which most of you know, so clearly it is communicable. And it's also very general, because whenever you need to calculate how much, for example, oil can these tankers hold, or how much gas I need to purchase to kind of fill all the basketball in a factory, you are using the formula for a sphere volume. And lastly, the kind of math he did later on developed into calculus, which may or may not be a source of frustration for you. So to recap, scientists are motivated by discovery that help people make predictions, and these predictors should ideally be easy to communicate, general, and can be built upon by others. So we covered what motivates scientists, which is to make good predictors, and what kind of work do they do to actually get at these predictors. Well, the form of predictor is kind of we call that a hypothesis, and it has a form of x goes to y. And in science, there are 2 kinds of, roughly speaking, hypotheses that we work with. There's one kind called predictive. So if I see x, I should expect to see y. So for instance, if I observe the ground is wet, I can maybe predict that it's also raining. But these kind of hypotheses are not causal. For instance, I cannot change y by changing x. So if I artificially make the ground wet by pouring water, I shouldn't be able to change the weather to cause it to rain. So you can only predict, but you can't change. And the other kind of hypotheses are causal. So those are the one that you could change. So the one example we gave before is causal. So if I plant rice now, I should expect that I will be able to get rice later. So these are the kind of hypotheses scientists typically work with. And the work they do is a kind of a cycle between using experiment to validate if a hypothesis is good, And once they check that the hypothesis is valid, they think about how they could explain this hypothesis to others. And they kind of go back and forth between the two. And it's different by domain, right? So a biologist might do this process differently from a computer scientist or a chemist. So that's the kind of work in general that scientists do, which is to make hypotheses that often have the form X goes to Y, and they do so by doing experiments and try to communicate these hypotheses once they're validated. So I'll talk about me now, the kind of work that I'm motivated by. So my motivation is that computers are difficult to use. It's much easier to tell another person to do something versus if you were to tell the same thing to a computer. So the work I do is to try to minimize the gap between how we talk to people versus how we talk to computer. So one day we can tell computer to do something as we would to another person and have the computer carry those instructions out. So that's my motivation. And the work that I do, I would describe. So to recap, the problem is to instruct computers in a human way and have them follow these instructions in a human way. The way I'm going to do that is to use something of imitation. So I'll give you an example. Here's an elephant. Elephants are very stable. What makes an elephant stable? Well, you can abstract it and say, well, perhaps this is because the elephant has 4 legs. And so we can apply this abstraction into other things to give them 4 legs, in which they will become also very stable. So how does that work for communication? Well, humans are very good communicators. So we'll kind of abstract the kind of principles that make human a good communicator. And so I'll give you an example. When I'm communicating to you, I'm building a theory of what you can or cannot understand. So if the audience, which most of you are English speakers, I would not try to communicate to you in Chinese because I knew that you wouldn't be able to understand. And so that's some of the mechanisms. And what we do once we discover these mechanisms is that we'll apply them into robots and machines, and so that they may follow instructions similar to how humans follow instructions. So it's the same imitation idea of abstract some principle and build system around these abstractions. So I will talk about some details on the experiments that I do and kind of how I typically present these works. So let's start with the experiment. My experiment is a kind of a loose term. It contains roughly 3 parts. So first is I will observe and kind of do studies on how humans communicate to each other. And then I will abstract some theory on what are the principles of human communication. And lastly, I build interactive system around these theories into things that people can actually interact with. So I'll start with the first one. Here are the kind of experiments that I do, which is asking people to instruct another to do some task. And here is, so maybe a quick cut. So I hope you can see this picture. Can you see? Okay, so I want you to think about how you might describe how to draw this picture to another person. So I've tried this with some high school students. One of the instructions they gave was this one. And I had another student follow this instruction to draw it. And this is what they drew. Okay, so these are the experiments that I do, which is very similar to the one we just did. Some of the experiments ask people to communicate analogies using words. Another kind of experiment asks people communicate designs using words and drawings. So what does that look like practically is that we make some website, and then we have some money, and we give both the website and some money to a group of people on the internet, and they do our experiments, and they give us data sets in return. So that's the first part. And what we do with this data set is that we would like to develop theory on how humans communicate from these data. And it involves typically categorizing some aspect of human communication. So in the experiment we just did with these shapes, we can say that, well, the communication would only work if you share some aspect of understanding what a square is and what a circle is and what a corner is, right? So these are the things that you can categorize. But to make communication work in robots, you want to formalize them using math. And so in practice, you end up having to write a lot of code and you have to do a lot of math. Okay, so last part, once we develop these theories on how humans communicate, we can build interactive systems around these theories. So here are some systems that I built. Some are systems that write program from human instructions, and others are things that manipulate objects from human instructions. So in conclusion, this is the kind of work that I do. I conduct and observe how humans communicate. And from these observations and data, I develop theories on how humans communicate. And lastly, I build interactive systems around these theories. Let's talk about presentation. How do you present your work? Something about the real world that's different from school is that nobody cares about you. So, unlike your teacher who are paid to read whatever you write, in the science world, you're trying very hard to get your audience to care. So what that might look like for a scientific paper is that you write a paper summarizing the kind of experiment that we described, and the scientific community would judge your paper based on the criteria that scientists care about, which is it general, is it easy to communicate, and would the rest of the community build on top of it, which is, does it make a good prediction? And if it does make a good prediction, they will say, that's good, please come present at the conference. So practically what that looks like is we would submit a paper that looks something like this, and you will get reviews. And note that the reviewers actually have a rate on their own confidence. If it gets accepted, you get an email that looks something like this, and they will say there is no reason to reject it. So it's very kind of defensive. Cool. Practically what that looks like is that you will go to a conference and present your work. If your work is not so popular, you will present it as a poster to a few dozen people around you. And if your work is very popular, you might present in an auditorium to hundreds of people listening to you. And there's another kind of writing that scientists do, which is a grant. So instead of a paper summarizing what you did, a grant is a plan for what you will do. And the funding source, if it's government, they will typically ask, does it make a good prediction? But if you're writing a grant to a company, they might also ask, would this idea help us make a lot of money in the future? And if they like your idea, they will give you some money to do your work. So that is a conclusion about what is it like being a scientist. Here are some pros and cons. The pro is that people pay you to think, and the con is that you're always thinking. Here's my resume for those who are interested. This is how I came to be a scientist. Yours will be different. Typically, not that many people want to be a scientist. So if you do want to be a scientist, you will find a way. This is how I spend my time. I just want a stand chart, okay? And here are some must-have skills. The only skill I would think is necessary is to be good at math. So just as you need some amount of muscle to do sports, you need some amount of math to do science. And a good way to do that is, in your undergraduate, try to consider a math double major or a minor. So in conclusion, being a scientist is fundamentally about changing the way people think. And the way in which you change the people think is to help them make better predictions about the future. And so in life, people will tell you how to think. This is unavoidable. It's impossible for you to discover how the world works all by yourself. And so other people will tell you, hey, here's how you should think. And how you should take that is, you shouldn't take it emotionally. Oh, this way of thinking make me feel a certain way. That is not very useful. What is more useful is you should judge if something that people tell you will help you make better predictions, as scientists do. And that is my presentation. And here are some questions that I was asked by students at the end, so you can read.